So we've been talking about electric potential, but it's been a minute since we saw each other. I've talked about that. It's been a week or so. Well, so I mean, yes. So the thing about approximations is they're your friend. Um, they make your life much simpler. They make this kind of proportional reasoning possible and easy. And it's one of the things you need to learn. So it is not always better to use the exact equation. Um, it is just fine. It is actually better to learn when you use approximations. You guys aren't uncomfortable with the approximations for the field of a dipole. You use that all the time. Well, when you're not told anything about L, you're going to have to assume that R is less than L. But otherwise, yes, there may be some gray areas, or there may be some situations where if the radius of the disk is 1 centimeter and you're 5 centimeters away, then obviously you're not close to the disk, right? So, but if you're, I don't know, there may be some gray areas, but really, if the distance is a tenth or hundredth of the radius or the length or whatever, it's fine, right? And I remind you that you're completely happy to use the dipole. So anyway, all right. So we're going to continue to run into these equations. So review. We talked last time about electric potential, which is electric potential, and which is energy per unit charge, potential energy per unit charge. So the units are joules per coulomb, and that has a name, which is volt, which is a capital V. And we will see shortly that there are devices that can actually measure potential in the real world. They're called voltmeters, and you unfortunately won't have them in your hands, but you'll at least kind of work with them in lab. We found that in the definition of change in potential, and the symbol is a capital V, okay, for volts, along some path, and when we talk about energy, we're always talking about initial and final locations or configurations, right? So along some path from an initial place to a final place inside a region of electric field, we found that in a uniform field, the change in potential we could figure out by just minus the dot product E with E and delta L, where delta L is now our symbol for displacement. So delta L is delta X, delta Y, delta Z in general, or whatever it is. And that if we knew a change in potential, then we could calculate the change in electric potential energy for a system that involved a charge being displaced from the initial to the final location along that path. So the change in potential energy of the system was the charge of the moving charge times the potential difference. And so this can be positive or negative depending on the sign of the potential difference and the sign of the charge. So both delta V, which is a scalar, right? So this is minus EX delta X minus EY delta Y minus EZ delta Z is what this comes out to. So it's a scalar. And the sign of potential difference depended on the direction of the path and the direction of the electric field. So we saw that if E is that way, if your path was in the direction of E, it came out that delta V was less than 0. If your path was opposite to the direction of E, then the potential difference was greater than 0. And if delta L was perpendicular to E, then potential difference was 0, and if it's some angle, you have to work it out. We will use the symbol. So in cases like this, delta means final minus initial. We actually have used delta E already in a situation where it didn't really mean that, because remember when we were adding up the electric field of things like a long charge rod or a long charge disk, and we divided the rod into pieces, and we calculated the contribution of one piece of the rod to the electric field, we called that delta E because it was a little part, a little piece of the field. So there is this other meaning of delta, which is a part of something, and we'll see that again. So today what we're going to do, and so there are now 2 homework assignments, one for last Thursday's lecture and one for today's lecture. They're due on Tuesday, and they relate to potential. So the first one is on last Thursday's lecture and what we've just reviewed, and the second one is on today's stuff. What we want to do is today is accomplish these things. I want to talk about notation. The notation we're using for denoting a potential difference between 2 locations, in particular the identifying the direction of the path, because we see that the direction of the path is very important. And so we have to get straight what this notation means. We want to, since not all situations have uniform fields, the field near a rod falls off like 1 over r, the field near a point charge falls off like 1 over r squared. We need to talk about potential difference in non-uniform fields. We want to establish the idea that potential difference is independent of path. So if you're going from some initial location to some final location, it doesn't matter how you get there, you're going to get the same potential difference. And that's really important. And that's related basically to conservation of energy round trip. And we want to talk about the meaning of potential of one location, which is related to all that. So first of all, though, let's see if we can remember anything here. So we've got the electric field is uniform in this region. We know the locations of points B and C. We're going along a path from C to B, and the potential difference is negative 500 volts. What's the magnitude of the electric field in this region? And so actually you seem pretty evenly divided, although it says that 4 is the most popular answer. They're really all about the same. And that can't be right. So let's see how we go about doing this. So we start with the definition. We have delta V is a minus E dot delta L. And so here it's going to be a minus E sub y, delta y, right? So this is going to be equal to and so we have a minus 500 volts is, well, E sub y is what we want to find out. And delta y is, so y here is 0, y here is minus 2, so delta y is equal to a 0 minus a minus 2 meters, which is equal to 2 meters. But really this is actually more work than we need to do. Since you asked for a magnitude, all we need to do is work with absolute values here. And so, so if we have 500 volts over 2 meters is the absolute value of E sub y, then that must be what? 250 volts per meter. Now, how would we write this potential difference? So we wrote here that, so we have delta V along a path from C to D is negative 500 volts. But how do we show in our notation that it's a path from C to D? Well, there are two ways to do it. We can have delta V, we can say, so we're going to B, so we could write B with a little arrow from C. A more common way to do it is to say that it's V sub B minus V sub C, where this is the final location on the path, and this is the initial location on the path. So our path, and I think it's really a great idea to always draw paths on diagrams so that you don't get that wrong. So that's going to be our delta L there. So this notation is, and that's equal to minus 500 volts, and that makes sense because the displacement is in the same direction as the electric field. We can make sure that works out by saying delta V is equal to, let's see, a minus E sub y is a plus 250 volts per meter, the same as newtons per coulomb, it turns out. And delta y we already figured out is a plus 2 meters, so we'd get a negative 500 volts. Now this notation, so this is important, the final minus initial, and we can write it more generally as delta V final, initial to final is V at some final location minus V at the initial location. Now this notation actually implies that the potential at a point has a meaning. Up to now we've just talked about differences here, and that's what we can measure. So that's usually the most interesting thing, because that's actually what our meters allow us to measure. But the potential at a point does have a meaning, and we will see what that is by the end of today. Potential difference is independent of path. Another way to say that is, so potential difference is independent of path. Is sort of equivalent to saying the round trip potential difference is, in any situation, is going to be 0. So if you start at A, go to B, C, D, and come back to A, it's going to be 0. And here's just a simple example that I think makes that a little clearer. So suppose we have our favorite situation with the uniform field, because we're inside a capacitor where the electric field is really almost exactly, and this is a big capacitor, so I'm not drawing it right, but the radius is much greater than the separation, the gap here. And so suppose we have some locations here. Here's A, here's B, here's C, here's D. So presumably we'd expect that if we went from A to B, and then B to C, and then C to D, and then D to A, we should end up, we added up all those potential differences, it actually ought to add up to 0. So we'd expect this, VB minus VA, that's the first one, plus VC minus VB, that's the second step, plus VD minus VC, the third step, plus VA minus VD, that's the fourth step, to equal 0. So let's actually just see an example of how this works out. Let's take our situation where we have 500 volt per meter electric field to the right here. And let's make this distance 2 millimeters. The distance between A and B is 2 millimeters, and the distance between B and C is 1 millimeter. And just see how that works out. So we have VB minus VA is going to be equal to minus EX delta X. So that's minus 500 volts per meter times 2 times 10 to the minus 3 meters, which gives us, let's make it 5,000 volts per meter just to make our life simpler. Okay. So that gives us a negative 10 volts, right? And now we're going to go from B to C. So we want VC minus VB is, well, this is going to be a minus EY delta Y, which is a minus 0 times 1 millimeter. So that's 0 volts. And we see the electric field here is perpendicular to our path. And now we have VD minus VC is a minus EX delta X. And so that's a minus 5,000 volts per meter times, now we're going backwards here. So that our displacement is in the minus X direction. So we have a minus 2 times 10 to the negative third meters. And so that gives us a plus 10 volts. And VA minus VD, now we're on the last leg of our path, is minus EY delta Y, which is a minus 0 times a negative. Oh, this should have been a minus here because we went down in Y before, but here now we're going up. So we have a plus 1 times 10 to the minus third meters, 0 volts. And so V sub A minus V sub A is 0 volts. Okay, so round trip potential difference is 0. How does that tell us that, how is that related to potential difference being independent of path? Well, consider going from A to C. So we want VC minus VA. So if we go from A to B to C, we get delta V is negative 10 volts plus 0 is negative 10 volts, right? So if we take this path and we go A to B and B to C, we get negative 10 volts. But there's another way we could go from A to C. Suppose we go from A to D to C. Well, so now we're going, let's see, let's make that green. So now we're going this way. And so we find that the delta V is, well, we're going to want VD minus VA plus VC minus VD. Well, we know that VA going from D to A gave us 0 volts, so that's going to be 0 volts the other way. We know that we have VD minus VC, so we know the potential difference going from C to D was plus 10 volts, but we're going the other way, so we're going to get a minus 10 volts here. And so we get a minus 10 volts, so it doesn't matter whether we take path 1 or path 2, we're going to get the same answer. Now this means, this has an interesting implication because it means when we're calculating a potential difference between two locations, we can take any path we want. So we could have actually taken a path, we could have just done a direct path from A to C here. And then we would have had two terms in the dot product to work out. We would have gotten the same answer. But instead, we can actually choose to go A to D to C or A to B to C if it's more convenient to calculate. So it turns it, so that's actually, we have to have a path, but it doesn't matter which one we choose. Okay, so let's consider a scenario where the field is not uniform. Now here's a simple case, just to consider a simple situation first, where we have kind of two capacitors back to back. So we've got we have three charge plates, let us say, which basically produce two capacitors. We can think of as two capacitors. So in this region here, we clearly have an electric field E1 going to the left, and over here, because this plate is positively charged, we have an electric field E2 going to the right. And suppose we want to know the potential difference between location A, which is here, we'll say X equals 0.3, and location B over here, which is X equals 0.6. And we know the magnitudes of these fields, so this is 300 volts per meter, and this is 200 volts per meter. So how would we calculate the potential difference between A and B? So we want to find VB minus VA, or delta V going to be from A. Well, we don't have a single value of the field, so we really can't use minus E dot delta L because this changes. So what we need to do is calculate the potential differences we know and add them up. So we're going to make this into a two-step path. So make path 2 steps. So instead of going from A directly to B, we have to invent a new point. So our new point is going to be a point C, and we're going to put it right there beside this middle plate here. And the middle plate is very thin here. And its location is 0.4 meters, okay? So now what we're going to do is we're going to say VB minus VA is going to equal the sum of these two steps. So we're going to go from A to C, VC minus VA. And then we're going to go from C to B. So we're going to have VB minus VC. And that is actually easy to do. So here now we can go back. Now we have uniform field over each step. So we can say it's minus EX delta X, which is a minus negative 300 volts per meter times 0.1 meters, since we're going from 0.3 to 0.4 meters in the plus X direction, plus a minus, now we have a plus 200 volts per meter, and we're going 0.2 meters in the X direction. And so here we get a plus 30 volts, which makes sense. Our path went opposite to the electric field for this first step. And in the second step, we should get a negative quantity because our path is going in the same direction as the electric field. So we're going to get a minus 40 volts. And so the overall potential difference is going to be equal to a negative 10 volts. Okay, so let's consider a situation where we can apply this. Here is a situation where we've got actually three regions of field. We have a region on the left where the electric field has a magnitude of 300 volts per meter, but it points to the right. So this region here. Then we have a region in the middle where the electric field looks like where E is 0. And in fact, since it's shaded, it looks like actually there might be a piece of metal here, some sort of conductor at equilibrium. And so the electric field is definitely 0 in there. And then over here on the right, we have another region, electric field pointing the other way. And so the first question is we want to calculate, so here's location A down here. Here's location A, here's location B. We know distances here. And so the first question is just if we're going to do this calculation, how many path segments should we use? All right, so here's what you said, and slightly over 50% say we should use 3 path segments, but about 45% say 2 path segments. So we are by no means unanimous here. So let's talk about this. If we use 2 path segments, where would the first segment go? So if we're going to use 2 segments, the first path segment starts at A, but where does it go to? So one person suggesting that our path would actually go to somewhere in the middle of the rod or something like that. Is that what you? Okay. So it is tempting to say we're going to take 2 path segments kind of like that. And the problem with that is that if we look at this one path segment here, it goes through 2 regions. It goes through a region where the field is 300 volts per meter and a region where the field is 0 volts per meter. And so the question is, if we're going to use E dot dl, what do we multiply? E, what do we use for E? And there is no value of E that's true in both of those situations. So that's, well, you can never omit a section of path, okay? That's, you have to account for all sections. You can't omit anything. So you can't have a broken path. The path has to be continuous. It can take as many steps as you want, but now what's going to come out, and I think you're seeing this, that the contribution of one of these segments could easily be 0, but you actually have to have all the segments, okay? So if you've got location A and location B, you've got to go there somehow. Your path might look like this. Can't loop back on itself, by the way. But you can't skip any locations. Yeah, okay, so in that case, we do need 3 segments, don't we? We need to go to the edge of this conductor, then we need a segment that goes across the conductor, and then we need to go from the other edge to B, because we have 3 different values of electric field that we have to use. Okay, given that, what's the answer? Number going from A to B. Okay, remember that signs are really, really, really important. So if you're sloppy about signs, you're going to get potential differences with the wrong signs, which means that your particles are going to be losing energy when they should be gaining energy, or gaining energy when they should be losing energy. So one of the details that you have to pay attention to here is be really careful about the signs of potential differences. It's okay, so we are very shaky on signs. The plus 6 volts and minus 6 volts are pretty much equally popular. So I think we probably better work it out. Now, I would argue here that you can actually tell by inspection what the sign of your answer should be. Because as you, I think many of you saw, the contribution from the path inside this conductor at equilibrium is going to be 0, because E is 0. But here we're moving 0.02 meters in the direction of the field, so that's going to be negative. Here we're moving 0.04 meters opposite to the field. That's going to be positive. The magnitude of the fields are the same, so the positive number is going to be bigger than the negative number, and so our answer should actually come out positive, but let's work it out. So we need a couple of extra points, don't we? We need a location C and a location D. So we have VB minus VA is VC minus VA, if that's the first step, A to C. Then we're going to go from C to D, and then we're going to go from D to B. And so this is going to be equal to a minus, so we have a plus 300 volts per meter is E sub x, and we have 0.02 meters. So this is VC minus VA. And so that gives us a, so 3 times 10 to the 2, 2 times 10 to the minus 2 gives us a negative 6 volts, right? And that makes sense because we're going with the field. VD minus VC is equal to minus 0 times 0.03 meters. So that's going to be 0 volts. And VB minus VD is equal to a minus, now the X component of the electric field is negative 300 volts per meter times 0.04 meters, which is going to give us a plus 12 volts. And so we add all these up and we get VB minus VA is equal to plus 6 volts. So it's worth taking the time to be careful about signs. Okay, try to ask a question. Well, no, volts is potential energy per coulomb. So it's related to work and energy, but it's on a per coulomb basis, just like electric field is a force per coulomb. So against the field is positive, yeah, and it always will be because here's our example. So from D to B, so we have delta V from end at B, start at D. So that's going to be a minus E sub X delta X. And so we have a minus, well, E sub X is a minus 300 volts per meter. That's E sub X. And delta X is plus 0.04 meters, right? And so we're going to get a plus 12 volts. It's easier to create an origin and axes. Sometimes we're going to be using R as a variable instead, you know, sort of polar, so the easiest thing is to use the standard coordinate system when you're reasoning about it, yes. But I mean, if you ran your coordinate system the other way or something, it wouldn't make any difference, because suppose you had plus X running to the left, then from D to B, your displacement would be negative, but the field would be positive. So those two signs would exchange, and you'd still get the same answer. So I think you need a coordinate system, and just stick to it. Yeah, you really do need to think about X and Y components. So basically, when we have, so what do? We use a procedure really similar to the one we use for finding the electric field of distributed charges. So we have to choose a path and divide into segments. Little delta L's. We have to find delta V, and the key is where you have a value for the electric field. Then you have to find delta V for each segment. You add it up, and then you check the sign, if nothing else. Does it make physical sense? So let's think about what we do with a point charge, the electric field of a point charge. So here's our point charge, and we've got a path, and here's location A, and here's location B. And we want to take a path. We want delta V is VB minus VA. So we're going to go from A to B. And really, it really helps to have a diagram and draw draw paths and draw fields. Now, and so we have some numbers here. We can say this is 2 millimeters, and this is 12 millimeters, and or whatever, but we're going in the plus X direction. So this is our delta L. But we have a problem here because the electric field of the point charge is actually varying a lot along here. So if this is the electric field at that location, when we get over here, the electric field is going to be much smaller. So if we just take an electric field at some location in the middle, we're actually going to get a really bad approximation of the potential difference because the electric field doesn't vary linearly with distance. It's falling off like 1 over distance squared, right? So to get this potential difference, what we need to do is indeed to give ourselves a coordinate system. And we're going to need to divide this path up into lots of little pieces. So let's for now, let's call this location R sub A, X sub A. Excuse me, and this is X sub B. So those are the locations of those points. And what we would do if we're doing it numerically is we divide up our path into lots of little pieces, lots of little delta L's, and then we calculate the electric field at the center of each one, and we calculate lots of little E dot minus E dot DLs and add them up. However, in this case, because we actually have we can write, we know we have an algebraic expression for the electric field of, calculus time. We have an algebraic expression for the electric field. We can actually use calculus to do it here. So we could write the electric field here as E is, let's see, we're going to use the standard coordinate system, X, Y, Z out. So it's going to be 1 over 4 pi epsilon 0, whatever the Q of the charge is, over X squared here, given our current coordinate system 0, 0. And one of our little delta L's, we're going to make them all the same size. So our delta L's are also just going to be a delta X, 0, 0. And then, of course, in the limit as delta X. So E dot DL in this case, so I'm getting it minus E dot delta L is going to be a minus 1 over 4 pi epsilon 0 Q over X squared delta X. And that's going to be true at any location X in the center of this. So we're going to have to, what we'd have to do is get all these E's here to add it up for one step. But we can convert this to an integral just by letting delta X get really small. So we can end up with our delta V is going to be minus the integral of E dot DL, which is 1 over 4 pi epsilon 0 q over x squared dx. And this is, of course, a finite integral because we're going from one path location to another. So to be more general, I'm just going to call this location, I'm going to call this final in that initial. So this is going to be x initial, and that's x final. So we're going from x initial to x final. And that's an easy integral because 1 over 4 pi epsilon 0 or q are just constants. So we're basically integrating, we've got the integral here of x to the minus 2 dx, right? And so what this comes out to is going to be, if we move some constants outside, we 1 over 4 pi epsilon 0, we've got a q, and then our answer is from that integral is a negative 1 over x. So negative x to the minus 1 minus 1 over x from x initial to x final. And we get, so that comes out to a plus 1 over 4 pi epsilon 0 q times 1 over x final minus 1 over x initial. And that's a general result, right? We don't actually have to do this integral again. Now we should check to make sure that the sign makes sense. So we said it should be negative because we're going in the direction of the electric field, so the potential should be decreasing. Okay, so you can think about a proton traveling along that path. Its kinetic energy would be increasing, so the potential energy of the system would be decreasing, so the potential's going down. And so so it should be negative. So let's see if it is. So x final is greater than x initial, the way we set up our coordinate system. So 1 over x final is actually going to be smaller than 1 over x initial, because if x final is 10 and x initial is 1, we have 1/10 minus 1. That's going to be a negative number. So in fact, this thing comes out to be less than 0, and so our potential difference is less than 0 if q is a positive charge, if this is a positive number here, if q is positive. If q was negative, the electric field would be pointing the other way, we'd be going against the field, and we'd get a positive potential difference, so that works out. So how would we use this? Well, suppose that q is that the point charge had a 3 nanocoulomb charge, and x initial was 2 millimeters, and x final was 12 millimeters. Then we'd just say delta V is equal to, we'd plug in 9 times 10 to the 9 Newton meters squared per coulomb squared times 3 times 10 to the minus 9 coulombs times 1 over 12 times 10 to the minus 3rd meters minus 1 over 2 times 10 to the minus 3rd meters to get our answer, right? And this gives us our most general definition of potential difference. So the potential difference between final minus initial is, so V final minus V initial is actually going to be expressed from R initial to R final negative the integral of E dot dl. And of course, if this works for a uniform field too, because in a uniform field, the integral of a constant is a constant. I mean, right? So that's going to work out either way. So we now have our general definition. We have in a uniform field, this is equivalent to minus E dot delta L. We don't really need to divide the path into segments. In our situation where we had to divide the path into 3 segments, that still works. We would have needed to evaluate each segment separately. And we have a result, which you do not need to memorize, that near a point charge, the potential difference was, which we calculated by integrating. It came out to 1 over 4 pi epsilon 0 q times, I'm going to write it as 1 over r final minus 1 over r initial, just because it might be in the y direction or whatever. Okay. So what does potential at a point mean? So what does what it really means is, it means V sub b minus the potential at infinity. So it means that if there's some charges over here making a field and you want to know the potential at location B, what you have to do is start over here at infinity and travel from infinity to B, calculating the potential difference along every step of the way. And when you get there, you add that all up, and that gives you the potential. Now, you start infinitely far away. We physicists like starting at infinity and marching in. Now, presumably, when you're infinitely far away from all these charges, the field is actually 0 anyway. But calculus comes to your rescue here again. So if we consider our example here, so here's our positive point charge Q, and here's location B. Well, V sub B would be the integral from the negative of the integral from infinity to r sub b of E dot dl. But we already know how to do this integral near a point charge. So this is going to be a 1 over 4 pi epsilon 0 q times 1 over r sub b minus 1 over infinity. And physicists are perfectly happy with 1 over infinity. We think it's 0. If you're a mathematician, you may want to think of the limit as r goes to infinity. And so the potential near a point charge would just be 1 over 4 pi epsilon 0 q over r sub b, where that's R sub B, right? Okay, so we're going to apply this in recitation this afternoon. What I'd like you to talk about in chat is something about the signs of potential differences, because that's come up as a confusing thing. So tell me what you understand about how you can predict the sign of a potential difference, or what you're confused about signs of potential differences, or why is r dot squared? Because we integrated. So the integral of 1 over r squared dr is minus 1 over r, right? Well, going against the potential, going against the field. Potential and field are different words here. Let's try to use, there aren't any synonyms in physics, so try to use words precisely. So force field and potential energy are all different things. Yeah, so I think the thing that may confuse you is that you have to think about paths. Okay, you really have to think about the path. Yes, that's sign of potential differences. So potential differences is indeed related to force, because potential is a change in potential energy per charge, right? So field exerts a force on a proton in the direction of the field. So if a proton travels that way, it speeds up, gaining kinetic energy, and therefore the system loses potential energy. So this potential energy of the system decreases when the kinetic energy increases, that kind of thing.